Okay. Now in class A operation, what I will do, first let me consider transformerless. Okay, transformerless, which is also called as series fed. Okay, series fed class A power amplifier. All right, fine. So this series fed class A power amplifier, basically works on CE mode, that is common emitter mode, and the biasing which is used for series fed class A power amplifier is fixed bias. So fixed bias is used. All right. So let us draw the circuit diagram. Okay. And remember, whatever transistor we are using in power amplifier, it is basically a power transistor. Okay. This is your transistor, base, collector, and emitter. So since it is using fixed bias circuit, so emitter will be directly held at ground potential. Okay, and then you will have the collector resistor RC, followed by the base resistor RB. Okay, and one side it is connected to VCC. Okay, and on the other side, the base terminal is being fed with an alternating signal. Okay, let's say this is your alternating signal, V in. Okay, so V in is the AC signal which is coupled across base and ground. Okay, and VCC is the DC power supply voltage. Okay, which is connected at the collector side. Okay, so let me mark the DC voltages and DC currents. Okay, say this is DC current IC and this is DC current IB. All right, and the terminal voltage VB measured from base to emitter terminal. Base is at higher potential and emitter is at lower potential. Similarly, we have VCE across collector and emitter. Once again, emitter will be at lower potential compared to the collector terminal. All right. So this is the circuit diagram. Okay. Now, as I said in the previous class, in case of power amplifiers, we will not consider RE model based analysis or H model based analysis. Okay, what we consider is called as the graphical based analysis. Okay, now in graphical based analysis, what we do is first we draw the transistor output characteristics. Okay. Okay, so let's say this is the transistor output characteristics. Okay. Let us consider the transistor output characteristics. Okay, let's say y-axis is your current axis IC. Okay, and your x-axis is your voltage axis VCA. Okay, as usual. And this is your transistor output characteristics, right? In common emitter configuration, this is how the characteristic curves look like. All right, so this is your transistor output characteristics. Okay, now in these characteristics, okay, let us select a Q point. Okay, let us select a Q point. Let me choose a different color. Okay, before that, Control Z. Okay, first let us construct the DC load line. Okay, so this is your output characteristics. Let me write output. Okay, okay. Next, let us write. first the DC operation. Okay, DC operation. So what I will do, these two things simultaneously I'm going to do the graph construction as well as the operation. Okay. So this operation is divided into two parts, DC operation and AC operation. That's because you have the power input as VCC. Okay. Now remember one thing, in case of power amplifier, power input is always PDC. Okay. And power output is PAC. Okay. Now why we are claiming that power input is PDC, even though we inject an AC signal at the base terminal. Okay, the reason as follows. In case of power amplifier, what you have to observe is that whether you couple the AC signal at base terminal or not. In the other words, okay, whether the signal is present or not at the base terminal, the power supply voltage, that is DC power supply voltage, is always connected to the collector terminal. So even in the absence of AC signal at the base terminal, the transistor constantly draws power from the power supply voltage. So on that note, in case of power amplifier, the power input is always PDC. Remember this. This is very, very important. And the reason I have already told you. Okay. Okay, this is very, very important. All right, so power input is always PDC because we need this particular information while calculating the conversion efficiency. So efficiency is nothing but the ratio of power output to the power input. And remember, power input is PDC in case of power amplifier. All right, so first let us take DC operation. Okay, so in DC operation, I can directly write an expression for base current, IBQ, right? What is IBQ? IBQ is VCC minus VBE divided by RB. Okay, so that's your IBQ. Once IBQ is found, you can find ICQ. So ICQ going to be beta times IBQ. That's your equation 2. Okay. And once ICQ is known to you, you can find out VCEQ. So VCEQ is nothing but power supply voltage minus the drop across the collector resistor, which is ICQ times RC. Okay. Now, remember one thing. In case of series fed class A power amplifier, the collector resistor RC itself, serves as the load resistor Rn. So that's the reason in different books, if you see, some books may take the load resistor as RC, or some books may take the load resistor as RL. Don't worry about it, okay? Or what you have to understand is that in class A series fed power amplifier, the load resistor itself is the collector resistor. All right. So just to be in line with. Okay, so what I will do, I will take this as RL. Okay, RL. So this is your third equation. Okay, so these are the performance equations. Apart from performance equations, you need to find out the load line. So you need to find out DC load line, right? Because there is DC current flow through the transistor as well. So to find DC load line, what you can do is substitute say VCEQ is equal to 0 in equation 3. That means to say short circuit condition we are assuming. So when you take VCEQ is equal to 0, you would get VCC is equal to ICQ into RL, or ICQ, okay, is equal to VCC by RL. Okay. Now, in order to avoid the confusion between the equation 2 and let's say equation 4, what you can do is let us just take this as some IC. Okay. We'll not take it as ICQ. We will just take it as IC. So what I will do, I will write 3A. So 3A going to be VCE is equal to VCC minus IC into R. So this I will take it as 3. Okay, all right. So you would get IC is equal to VCC by RL. Now remember, this is the maximum collector current that can flow through the transistor. Hence, this is also taken as IC saturation. Okay. These are all known things to you. Okay. Similarly, substitute. Now put IC is equal to 0 in equation 3A. Okay, what do you mean by IC is equal to 0? It is analogous to open circuit, because in case of open circuit, current becomes 0. So what do you get? VCC is equal to VCE, and since this is the maximum open circuit voltage that exists across the transistor terminal, so you can take this itself as VCE saturation. VCE saturation. So IC going to be your y-intercept in your transistor output characteristics, and VCE going to be the x-intercept in the transistor output characteristics. So now that you have found IC saturation and VCE saturation, what you can do is you can locate those 2 points in the transistor output characteristics. Say this is your IC saturation, and say this is your VCE saturation. All right, and just join the 2 lines. Join the 2 lines. All right. So that's your DC load line. Okay. Now in the DC load line, this is your DC load line. Let me just write it. Load line with the slope as m is equal to minus 1 by RL. Why? Because the slope is decreasing in nature, right? So that's the reason negative sign you will have to incorporate, and the slope is equal to 1 by RL, where RL is the value of the load resistance. Okay, so at the center of the load line, let us choose the Q point. Okay, so this is your Q point, and what are the coordinates of Q point? The coordinates of Q points are ICQ and VCQ. Okay, so let me write the coordinates as x comma y, right? So x coordinate is VCE and y coordinate is ICQ. This is your what you say, the load line. Okay. Okay, since I need some space, so what I will do, okay. Okay, all right. So I need some space. That's the reason, I have little shifted the analysis part, because I need to draw the graph as well. Okay, all right then. So this is your graphical analysis. Now, in order to draw the waveform, okay, what we can do is you can select 2 lines, one above the Q point and one below the Q point, towards y-axis as well as towards x-axis. Okay, so this is how it is done. Okay, so what I will do, I will select 2 equidistant points. Okay, from on the transistor DC load line, and then I will draw the thin lines. Okay, so from the top point and from the bottom point, sorry, the middle point, and then from the bottom point. Okay, the same thing I need to do it along y-axis also. middle point is already projected, so no worries. Okay, so once this is done, you can draw the waveform. So collector current waveform, let me draw. So this is your collector current, and this is your output voltage. Output voltage. Okay, so this is the positive half cycle. Okay, so for the positive half cycle of the collector current, you are going to get the negative half cycle of the voltage. Okay, that's because the transistor is driven in common emitter configuration. All right, so this is your the waveform. Okay, let us also mark few important values of these waveforms. So this is the maximum value. Okay, and this is the minimum value. Okay, this is the minimum value. Similarly, this is the maximum value of the output voltage, and this is the minimum value of the output voltage. All right, and this is called as VM, right? So this is the VM distance. Similarly, this is also VM. Okay. On the other hand, if you were to measure the distance between the two peaks, you would call it as V peak to peak. And remember one thing, V peak to peak is 2 times the maximum value. Okay. Similarly, this particular distance going to be I peak to peak, which is equal to 2 times IM. Okay, so in future, okay, when we discuss about the efficiency, etc., we would be needing these equations. Okay, IPP and VPP. That's the reason at this point itself I have shown the location of VPP and IPP and how to measure VPP and IPP. All right, fine. So that's about the graphical part of it. Okay. Now let us get into the expression for conversion efficiency. Okay. So to find expression for conversion efficiency, first let us define the efficiency. So conversion efficiency is defined as ratio of power output to power input. Okay, in case of power amplifier, the power output is P0 AC and power input is PI DC. Okay, because I have already told you why the power input is considered as PI DC. Okay, where PI DC is nothing but the product of current into voltage. So voltage is power supply voltage and current is ICQ, the collector current. Okay, so this is your expression for PIDC. All right. Next, let us write an expression for AC signal. Okay, so AC power output. P0 AC. All right. Now, to write an expression for AC power output, okay, you can use different terminologies. For example, if at all you want to represent the voltage signal, you can represent the voltage signal in terms of maximum value, or you can represent in terms of peak to peak value. Okay, or you can also represent in terms of Vmax and Vmin value. Vmin value. Okay, now let us try to understand how exactly we can, get the expression for AC power output in terms of maximum, peak to peak, and max min values. All right. So first, let us define the different voltages. Say V min. Okay, V min is equal to minimum value of instantaneous collector output voltage. Okay, that is collector to ground, which is nothing but VCE. Similarly, V max is equal to maximum instantaneous value of collector to output voltage. Okay, and then we can also mention VPP. VPP is peak to peak value of AC output voltage across the load. Okay, which is nothing but the collector output voltage. Don't have to worry about it. Okay, now what is peak to peak? Okay, peak to peak voltage is nothing but difference of the maximum value and the minimum value, right? V max minus V minimum. Okay. Then we can also mention VM. VM is nothing but the amplitude of output voltage, okay, which is actually V max itself for a symmetrical waveform. Okay, so you can write that your maximum voltage, okay, is, or you can say peak to peak voltage is 2 times the maximum voltage, or the maximum voltage is basically peak to peak voltage divided by 2, okay, which is also equal to, what is peak to peak? Peak to peak is V max minus V min divided by 2, okay. Fine. Similarly, you can also write maximum value of current as peak to peak current value divided by 2, or I max minus I minimum divided by 2. Okay. So let us take this as the current expression. Okay, this has the current expression. Okay. So once we have denoted Vm and Im, we can define the voltages in RMS values. So let me write in terms of RMS values. You can write Vrms is equal to maximum by root 2 and IRMS is equal to maximum by root 2. Okay, all right. So let's take this also. Okay. And now you can write down the expression for power. Expression for power. So first let me use the RMS values. So using RMS values, you can write the expression for power as P naught AC is equal to Vrms into IRMS, right? Or you can also write it is something like I square RMS into RL. Okay, that's because you can always mention that voltage is equal to current into resistance, where RL is the load resistance. Okay, or you can also write the expression for power in terms of voltage, that is Vrms square divided by R. This is P naught AC. All right, so this is in terms of the RMS values. Okay. Next, you can write in terms of peak values. Let me write in terms of peak values. So in terms of peak values, what you can do is, first you can write down the RMS value expression. So P naught AC is equal to VRMS into IRMS. Okay. So peak values, right? So you can substitute the peak or maximum one in the same. So VRMS is equal to VM divided by root 2 into IRMS is equal to IM divided by root 2, or it is basically VM IM divided by 2. Okay. So once you have this, you can write down the other variants, right? So for example, VM, you can write it as IM into RL. So IM into RL into IM divided by 2, or it is basically IM square into RL. Or you can also write something like VM square divided by R. Okay, so this is also P naught AC. P naught AC. So you can also write an expression for power in terms of the maximum values. Okay. The third one, pretty interesting one, is in terms of peak-to-peak values. Okay, using peak-to-peak values. Now, to write an expression for AC power in terms of peak-to-peak values, what you can do is you can exploit the previous relation, that is, we have seen in terms of maximum values, power can be written as Vm Im divided by 2. Okay. Or now, what is Vm? Vm is basically half of the peak-to-peak voltage value, right? So it is VPP divided by 2 into Im is half of the peak-to-peak current value divided by 2, or 2 into 2, 4, and this 4 comes to the denominator becomes 8. So 8, okay, stays in the denominator, and in the numerator you will have VPP and IPP. Okay, so this is the expression for power in terms of, the peak-to-peak values. Of course, you can also write P naught AC is equal to, you can write IPP square into RL divided by 8, or you can also write VPP square divided by RL into 8. Okay, so the different variants. But we know that, okay, V peak to peak is equal to V max minus V min, and I peak to peak is equal to I max minus I min. Okay, say this is B and say this is A. Okay, so what you can do, substitute B in A. So when you substitute equation B in equation A, you will get a very typical form of AC power, which is P naught AC is equal to VPP. What is VPP? Max minus min into I max minus I min divided by 8. This is the expression for power. All right, in terms of maximum and minimum values. Now, I would say this is the very important, expression when it comes to the calculation of efficiency. I'll tell you. Okay. So therefore, conversion efficiency. Therefore, conversion efficiency of a series fed class A power amplifier is equal to eta is equal to P naught AC, that is the power output, divided by power input, right? So what is P naught AC? P naught AC can be substituted from this particular equation. So you can write it as V max minus V min into I max minus I min, okay, divided by 8 into P in DC. What is P in DC? VCC into ICQ. Okay, ICQ. So this is the expression for power. Okay, in terms of percentage efficiency, what is that you should do? You should multiply by 100. Okay, this is the expression for power. Okay, fine. Next we have the expression for maximum efficiency. In bracket, let me write eta max. Okay, in any physical device, it could be an electric machine or it could be any other electronic circuit. You can also try to find out something known as what could be the maximum efficiency given by that particular device under optimum conditions, right? So similar to that, you can find out the maximum efficiency for a power amplifier as well. Okay, now in order to find the expression for maximum efficiency, firstly what I have to do is I have to recreate the load line characteristics. Okay, so let me please give me some time to reconstruct the load line characteristics. Okay, I'm not going to draw the output characteristics, I'm just going to draw the load line, that's all. Okay, so let's say, let me draw bigger scale. Okay, say this is your load line. So this is your load line. Okay, so this is your IC saturation, and this is your VCE saturation, and your X variable is VCE and Y variable is IC. Okay, and let us also mark the Q point. See, at the middle, let us take the Q point. Okay, so this is your Q point. Also write on the coordinates of Q points, which are VCEQ and ICQ. All right. Now, let me write it somewhere here. Okay. Okay. This is very important. So, the maximum efficiency comes into picture when the maximum efficiency comes into picture when the maximum swings of IC and VCE is allowed in the device. Okay. So the maximum efficiency comes into picture only if you allow the maximum signal to flow through the device. Okay, you should allow the maximum current to flow and you should allow the maximum voltage to appear across the load terminal. So this is the condition for maximum efficiency. Okay, now let me take you back to the previous graph. Okay, now in the previous graph, okay, if you look at the collector current waveform and the voltage waveform, you would see that you haven't allowed the waveform to reach to its maximum limit. Now, what is the maximum limit? See, the maximum limit is nothing but ice saturation for the positive half cycle and the zero value, okay, or the reference x-axis in the negative half cycle. Okay, so that means to say, this should have been the maximum swing for the collector wave, and also along the x-axis, the limit for the maximum output voltage swing is between VCE saturation, which is VCC, and the origin point, which is at 0 volt level. So this should have been the maximum swing for the output voltage. Okay. However, while calculating the efficiency, we never considered the maximum swings. We considered, a kind of finite swing. okay, wherein your collector current was toggling between I maximum and I minimum value, right? So maximum value is here and minimum value is here, and you can clearly observe that this maximum value is not coinciding with the collector current saturation value. Okay, so that's the reason while calculating the efficiency, what we are trying to do is that we are trying to allow the maximum current to flow through the collector terminal, and we are also allowing the maximum voltage to appear across the collector to emitter terminal. All right. So what we will do, we will draw some thin lines. Okay. See, from this point, and then from this point. Okay. And then let us draw also from this point. Okay, so this is for the collector current swing. Similarly, let's do it for voltage swing. So draw a point from here. Okay, and then from the Q point. These are all the guidelines, okay, for us to draw the maximum collector swing and maximum voltage swing. All right, so now that we have drawn the reference line, you can draw the signals. So this is the maximum collector current signal that can flow. Positive half cycle and the negative half cycle. Similarly, negative half cycle of the output voltage, and then comes the positive half cycle of the output voltage. All right, so the maximum point, okay, so let's take this as I max, okay, which is I saturation basically, and this is our I minimum. Okay, what is the value of I minimum? It is 0. Okay, and remember one thing, what is the distance measured from the Q point reference and the x-axis reference? It's ICQ, right? This is ICQ. This point is ICQ. So from 0 to this point, 0 to Q point, the distance is ICQ. If that's the case, then what is the distance measured from the top line and the bottom line? It is 2 times ICQ. So this distance is basically 2 times the ICQ. Okay. So I max is IC saturation, and IC saturation is at 2 times the ICQ level. So let me write, it is 2 ICQ. I hope this is clear. So I max is equal to 2 ICQ and I minimum is equal to 0 amperes. Similarly, this VCE saturation is VCC, right? So this is the minimum voltage, Vmin. Okay, it is at what level? 0 voltage level. And this is the maximum voltage, V maximum. Okay, this is at what level? VCE saturation level. Okay, which is at VCC level. Okay, so V max is at VCC and V minimum is at IC maximum. Okay, then you can write down the expression for P naught ESC. First, let me write what is P naught ESC, or rather Control Z. Efficiency relation, let me write. So we have already written in terms of max and min values, that is V max minus V min into I max minus I min divided by 8 into VCC into ICQ. So eta max is equal to, okay, you need to substitute the corresponding values. So for eta max, what is the maximum value of Vmax? Vmax is VCC minus what is VCE? Minimum. Minimum is 0 into what is Imax. So Imax we have already seen. Imax is at what level? 2 ICQ level, right? So it is at 2 ICQ minus I minimum. I minimum is 0 because the lower point coincides with the origin, so origin is at 0 into VCC into ICQ. Okay, so let's rewrite. We can eliminate the 0 values there. So VCC into 2 times ICQ divided by 8 into VCC into ICQ. So VCC, VCC, ICC, ICQ gets cancelled. So it is 2 by 4. So eta max is equal to 2 by 4 or it is 1/4. Okay. Therefore, the maximum percentage efficiency that can be obtained from a series fed class A power amplifier is about 25%. So this is the expression for maximum efficiency. That's what I was trying to tell you in the beginning, right? Even though you are getting a complete 360 degree, even though you are getting a complete 360 degree distortion-less output, right? You see, there are no distortions. You will get a perfect 360 degree output waveform. Though your output is not suffering from any distortion, the conversion efficiency is found to be very, very low. That is about 25%. So that's the reason, you know, class A power amplifiers are seldomly used in practice. Okay, so you want a power amplifier which can give you higher conversion efficiency. All right, so that's the drawback of series fed class A power amplifier. And remember, this is the maximum efficiency. Then imagine the realistic efficiency. The realistic efficiency will be a lot lesser than 25% level. All right, fine. So this is the end of the efficiency discussion of class A power amplifier. So in exam, if at all you have been asked to explain class A power amplifier, you know, you have to draw the circuit diagram, draw the waveforms, and write down an expression for efficiency in terms of max and min values, and then substitute the respective max and min values to get the expression for the maximum, you know, conversion efficiency. All right. Fine. Now, sometimes in numericals, you will be asked to find out what is the power dissipation like. Okay. So some short equations I can write. Power dissipation. Okay. So what is power dissipation? Power dissipation is nothing but the amount of power which is not being converted into AC. Correct. You will take some X amount of power input, and using this amplifier circuit, you will produce Y amount of power output. Okay. So the leftover power, that is X minus Y watts, is nothing but the power wasted or power dissipated in the transistor. Okay. So expression for power dissipation, okay, we can write it as PD. So PD for power dissipation is equal to the difference of input power minus difference of output power. So difference between input and output is the power dissipation. So with respect to our, you know, amplifier, we can say power dissipation PD is equal to PI DC minus P naught AC. So this is the expression. Okay. If you can calculate what is PI DC and what is P naught AC, you subtract the two and you will get an expression for power dissipation. All right. Fine. Next, you also have something known as the maximum power dissipation. Maximum power dissipation. Now, just by looking into the equation A, you can say, I mean, you can write down the expression for maximum power dissipation. Okay, if the AC part of equation A were to be 0, then your power dissipation going to be maximum. Okay, so when P naught AC is equal to 0, okay, the maximum power dissipation occurs. Power dissipation occurs. Okay, so is it possible? Can you have an instance at which P naught AC is equal to 0? Okay, I can just elaborate this particular case. Okay, let's say this is your public addressing system, PAS, black box. And let's say this is your power input. Okay, I'm talking about, and this is say your power output, P naught AC. Now, what I'm trying to tell you is that what if, I mean, when this power output is 0 watt, I'm saying that the PD max or maximum power dissipation occurs. Okay. Now, when can you have the AC power 0? When your AC input is 0. When your AC input is 0, then output AC is 0. Okay. I mean, AC power is 0. Okay. Let's say this is your microphone, condenser, whatever you call it. Okay. Let's say this condenser is connected to the public addressing system. Okay. So whenever, okay, so looks like Elvis Presley. Yeah. Whenever, you utter voice commands, the public addressing system picks up the voice input and gives out the AC power output. Okay. On the other hand, if no voice input is given in the sense, if you don't talk anything in the microphone, will you be able to get any sound output at the speaker terminal? No, right? The sound signal going to be 0. So that is the condition at which P naught AC will be 0. So when P naught AC is 0, PD becomes maximum, and the maximum power dissipation occurs under 0 AC input condition. So PI DC it is going to be. So this happens under, you can write under 0 AC signal condition. Okay, so that's the expression for maximum power dissipation for a class A power amplifier circuit. Okay, now let us talk about the merits and demerits, or in other words, advantages and disadvantages. So advantages of series fed class A power amplifier. Okay, there are many advantages. The biggest advantage is that simple circuit, and hence the design is it's a simple circuit. In the sense, it is consisting of less number of components, hence the design is simple. Since it is having less number of components, you can say that circuit is circuit is compact and less bulky. Okay, less bulky. And since it is made up of less number of components, cost is very less. The cost is very less. Okay, so these are the major advantages. Okay, advantages. Now let us talk about the disadvantages. The first disadvantage is that the very poor conversion efficiency. The next disadvantage is that high power dissipation. Okay, though point number 2 is derivative of point number 1, no harm done. Okay, you can always say that power dissipation is quite high. Okay, And the third disadvantage is that impedance matching is very poor. I will elaborate on this particular point sometime later. Impedance matching is poor.